Welcome to the first lesson in our matrix unit. Our goals today are to basically define matrices, but also look at just some really basic operations. And these are the types of things that you might see on your ACT or SAT tests. So this could be really useful if you encounter a matrix question on a standardized test. So a matrix by definition is just a rectangular array of numbers. Each entry in the matrix will have a location based on the row and the column that it is located. So a matrix must have entries for every position, okay? It must be a complete rectangle. We name a matrix with a capital letter. So you'll see in the matrix below, this is the name of that matrix. Any letter we can use except for O and I, which have specific meanings, which we'll see in some of our lessons in the near future. But a matrix is made up of a bunch of different numbers. So you won't see like A11, A12. You're going to see like the number 10 or 3 or -5 or so on. But what we're seeing here are the ways we can name each of the elements in that matrix. So A11 is a special place of saying that is the element in row 1, column 1, which brings us to the next part of matrices, which we call the order of a matrix. It's also called the dimensions sometimes. You might hear someone say, you might hear the word dimensions instead of order, but a matrix is described as rows by columns, where we start with however many rows there are, followed by however many columns there are. So a row, this is a row. Okay, a row is horizontal, and a column would be something like this. It's vertical. So if I'm going to name a matrix, I need to count up the number of rows there are first, and then count up the number of columns. So in the three matrices we see below, if we wanted to name these matrices by their order, we would say how many rows are there and how many columns are there. So I see 1, 2 rows, so I would name this a 2 by, and then I see 1, 2 columns. It's a 2 by 2 matrix. That's the order. In matrix B, I see 1, 2, 3, 4 rows, and I see 1, 2 columns. So this would be a 4 by 2 matrix. In matrix C, I see 1 row and 1, 2, 3, 4, 5, 6 columns. So it's a 1 by 6 matrix. So what's the difference between a 2 by 3 and a 3 by 2 matrix? So go ahead and draw some pictures below to show that illustration, and I'll take a look at those in class. I'll probably have you share them with me in class. So pause the video here and draw your pictures, and then we'll move on. Adding and subtracting matrices is probably one of the easiest operations that you can do with a matrix. However, you have to make sure that your matrices have exactly the same order, okay? So if they don't have the same order, you cannot do an addition or subtraction. So for example, we can add a 4 by 5 matrix to a 4 by 5 matrix, but we cannot add a 4 by 5 matrix to a 5 by 4 matrix, okay? When we add and subtract, we're going to add and subtract the elements that are in the same position in each of the two matrices. So just to show you what that looks like, let's go ahead and go through these 4 addition and subtraction problems, all right? So number 1 says let's add A plus B. So we're adding matrix A, 0, -1, 3, 4, to matrix B, which is 5, 4, -3, 1. Now our dimensions are the same in both. Both of these matrices, look, it's a 1, 2, 1, 2. A is a 2 by 2 matrix, and so is B. And that is how we can add them together. They have to be exactly the same, because here's how this works. I'm going to take something from matrix A, so I'm going to take the first element of matrix A, and I'm going to add it to the first element of matrix B. So I'm going to add 0 plus 5. Then I will take the the second element in matrix A and add it to the second element in matrix B. And that's going to go in the same position it was in the original matrix. Then I'm going to take the third elements and add them together. So I'll have 3 minus 3. And then finally, I'm going to take the last elements in the matrix and add them together. So 4 plus 1. And just notice that the original position of the two pieces that you're adding together becomes the final position of the sum in the matrix at the end. So I'm going to add 0 plus 5. I will get 5. Add negative 1 plus 4. I get negative 3. 3 minus 3 is 0. And 4 plus 1 is 5. That matrix is my sum. So this would be my answer. Okay, let's try, how about you try B plus A? So go ahead and pause the video and you try adding B plus A together and come back and check your answer. All right, so here's what you should have ended up with. And I hope that you notice these two are identical. So we're starting to kind of learn some things about adding matrices here. We can add them in either order and we get the same result. Let's talk about subtraction now. So let's do subtraction. The first one we'll do together. So A minus B. Okay, so I'm going to take matrix A and I'm going to subtract matrix B. So let's see. Matrix A is 0, negative 1, 3, and 4. And matrix B is 5, 4, negative 3, and 1. And I'm going to subtract those from each other. So to do so, we're just going to do the same thing we did before. We're going to take each of the elements in their positions and subtract from the same position in the other matrix. So in other words, I'm going to do 0 minus 5. Then I will do negative 1 minus 4. Then I'm going to do, now watch this one, 3 minus negative 3. And then 4 minus 1. And then we just have to simplify that. So when I simplify that, let's see, 0 minus 5 is negative 5. Negative 1 minus 4 is negative 5. 3 minus negative 3, that's actually 6. And then 4 minus 1 is 3. So I get this matrix. That's my answer. I want you guys, pause the video. Now you try the fourth problem here, which is B minus A. Come back and check your answer. All right, so now if you look at these two, they're not exactly the same. They're not entirely different, but they are not equal to each other like we saw with the sum. So what we should notice is that A plus B is the same as B plus A, but A minus B is not the same as B minus A. What we are seeing here is what we call the commutative property for addition, and it holds for addition but not for subtraction. So order, when we're adding, the order of the matrices will not change the final sum. All right, so now we're going to add in a third matrix, matrix C, and if we want to try to add this to the other matrices, we do need to make sure that it has the same dimensions, and it does. It is also a 2 by 2 matrix. So we're going to just do some operations here. So let's do A minus B minus C. Now the parentheses are really important, versus A minus B minus C. I will do A minus B minus C with you, the first one, and then I'll have you pause the video and try the second one. So what we'll have is matrix A minus matrix B. Let me spread that out just a little bit. And we're going to do that first. That's what the parentheses mean. And then we're going to subtract matrix C. Okay, so the first thing I'm going to do is subtract A and B, right? And we did that on the first page, but let's go ahead and do that here again. So A minus B is going to be 0 minus 5, which will be negative 5. Negative 1 minus 4, which is negative 5. 3 minus negative 3, which is 6. And 4 minus 1, which is 3. Now we've done what's in the parentheses. Now I go ahead and subtract matrix C. So I'm going to have negative 5 minus negative 2. So that's just negative 5 plus 2, which is negative 3. Then we'll have negative 5 minus 4. That's negative 9. 6 minus 2.3. That's 3.7, and 3 minus 1.6 is 1.4. So that's what we get when we take A minus B first and then subtract C. All right, now I'd like you to pause the video and try the comparison. So try A minus and then in parentheses B minus C. Okay, so when we compare the two, they're obviously different. So the order in which we do things matters, especially when we're talking about subtraction. This is called the associative property. Again, this will hold for addition, but when we throw in subtraction, it will not hold. In other words, the associative property states that you can add regardless of how the numbers are grouped. And when we say grouped, we're talking about where the parentheses are. So in other words, it doesn't matter where you put the parentheses because the outcome will be the same. That's just for addition, right? Because when we do subtraction, as we saw up above, it obviously will have an impact on how the final difference is. All right, next up we're going to talk about scalar multiplication, which is directly related to the distributive property. A scalar multiple is just a single number that we will use to multiply a matrix by. To perform a scalar multiplication, we will simply distribute that scalar to all the values within the matrix. And the distributive property we've seen many times in algebra states that we can multiply a sum by multiplying each of the parts of the sum separately and then adding the product. So an illustration of the distributive property, sorry about that, is right here. 5 times x plus 3 is the same as saying 5x plus 5 times 3, which we know ends up being 5x plus 15. So we're going to do two things here. We're going to first find 1.3 times a. Now we're going to write it like this. 1.3 times a. Okay, that's how we would write a scalar multiplication. And then we're also going to do negative 1/8 times b. Now b is a matrix we have not yet encountered. B is a matrix that is a 1 by 3 matrix. Okay, so we will not be able to add a and b together, but we can perform these scalar multiplications on each one. So how this works is I'm just going to take that 1.3 and I'm going to multiply it just like we would if it were a set of parentheses. I'm going to multiply it times everything inside that matrix. So I'm going to multiply 1.3 times negative 1. That gives me negative 2.6. I'm going to multiply 1.3 times 4. That's going to give me 5.2. I'm going to multiply 1.3 times negative 2. That's negative 2.6. And I apologize. You guys are probably wondering where I got that number from. That is just negative 1.3. Sorry about that. And then negative 1.3 times 0 is just 0. So we end up with this is our product. With negative 1/8 times matrix B, again, we're just going to multiply it by everything inside the matrix, and we end up with a matrix that's the same size that it started out as. So we'd have negative 1/8 times 0 is 0. Negative 1/8 times 4 is positive 2. And negative 1/8 times negative 2 is negative 1/4. Okay, and we end up with that as our product. All right, let's put all of this together. So I'd like you guys to try this one. I'll have you pause the video again and try it. You're going to do 2a times 2 times a minus 8 times b plus 3 times c. Okay, so you're going to have to multiply everything by their scalar multiple first, and then add and subtract things from left to right. All right, so let's see what you come up with, and I'll have the work shown for you when you come back. All right, so all of the work is shown, so if you need to take a moment, pause the video here, and double check your work. But this at the end is our answer. Notice a couple things as we're looking at this. The first thing I did on each of these was I took care of that scalar multiple. So I actually went through and multiplied everything by the scalar multiple. Now, you'll notice I multiplied just by positive 8 here. All right, you could have multiplied everything by negative 8, but that would change this to a plus sign then. So just keep that in mind. You may have done that, and that's okay. But we have to follow order of operations, right? Multiply, get rid of your parentheses first, which in this case means distribute that scalar multiple, and then add from left to right. So we do need to make sure we add or subtract these two things first, and then whatever we get from that, we add to the final matrix. All right, so our final piece of the puzzle today for our introduction is what we call the zero matrix. We use O to label this matrix. It's also known as the additive identity for matrices that have the same order. So what that means is if you add the zero matrix to any matrix, we're always just going to get the original matrix. Okay, as long as the zero matrix has the same dimensions as the original matrix. So these are different examples of your zero matrix with different dimensions. So here, our first one, we have a 3 by 3 matrix. Here we have a 3 by 2 matrix. Here we have a 2 by 3 matrix, and here we have a 1 by 6 matrix, I believe. So we can add, we can have an additive identity. We can have the zero matrix with any dimensions, okay? Last thing we're going to do here today, and this is specifically because we see problems like this show up on the ACT and SAT all the time. We're going to solve for x in the equation below, given the following matrices. We're going to use that concept of the zero matrix to help when we get to part B. So for the first matrix, we want to figure out, or for the first equation, we want to figure out what matrix X is. Now, in order to find that, we have to take 3 times matrix A plus 2 times matrix B. So kind of like what we did on the previous couple of problems. So matrix X is just going to be what we get when we add all that together. So I'm going to first distribute my 3. So that'll give me 0, -3, 9, and 12. And then to that, I'm going to add what I get when I distribute the 2. So 10, 8, -6, and 2. And then I just add those together. So 0 plus 10 is 10, -3 plus 8 is 5, 9 minus 6 is 3, and 12 plus 2 is 14. So matrix X is just 10, 5, 3, 14. Now part B, a little bit different. So let's look at how this is different. So I take -2 times matrix A. Now that is equal to negative B. So it's like saying -1 times B. Okay, so I can think of that as -1 times B plus X. Now imagine we wanted to get this equation solved for X, right? We're going to eventually have to subtract something or add something to both sides. So let's go ahead and kind of clean this up a little bit. I'm going to multiply everything by my -2. So that's going to give me 0, -6, +2, -8, equals, now I'm going to multiply everything by -1. So -5, 3, -4, -1, plus X. Again, remember we're trying to solve for X. Now in order to do this, we're going to have to basically subtract what we have on the right side so that we can get X by itself. So we're going to subtract matrix, whatever that purple matrix is. All right, so what I'm going to do is I'm going to say, well, let's take, let me do this. On the right side, I'm going to take -5, -4, 3, -1, and I'm going to subtract that exact same matrix here, okay? Now, that is no different than if we were solving an equation, except I have to make sure that whatever I do to one side, I do to the other. So I have to subtract that same matrix from the other side. So what we end up with on the right side is 0, 0. We end up with the zero matrix plus X. Okay, and then we have on the right side, or sorry, on the left side, 0 minus -5 would just be adding 5. 2 minus -4 is going to be 6. -6 minus 3 is -9, and -8 minus -1 is -7. And at this point, guys, what we've been able to do is basically get X added to the zero matrix. So we know that because of that additive identity piece we talked about up there at the top, that X plus the zero matrix is just going to end up being X. And what we end up with is that X is the matrix 5, 6, negative 9, 7. Okay, as always, let me know if you have any questions. We'll probably be in class together after you're done watching this, so just let me know if you have any questions in class and we can talk about them together.